Hello everyone, my name is Anvesh from Electronics and Communication Engineering Department, B section with roll number 620240, and today we'll be discussing the secant method. But before we get into the main topic, let's briefly discuss Newton's method. Newton's method is a numerical optimization algorithm used to find the roots, minimums or maximums of a function. The Newton's method uses the derivative of the function to find the root by approximating it with a tangent line at an initial guess. It iteratively refines the estimate of the root until a desired level of accuracy is reached. However, Newton's method may fail if the derivative is 0 or undefined at the root, or if the initial guess is not close enough to the actual root. This is where the secant method comes in. The secant method, on the other hand, uses the slope of the secant line between the 2 points on the function to approximate the root. It starts with the two initial guesses, computing the slope of the line between them to estimate the derivative, and then repeats the process until the desired level of accuracy is achieved. This method is useful when the derivative is difficult to compute or not differentiable, but can converge more slowly than Newton's method and requires careful initial guess selection. Talking about the methodology, we know that the secant method involves using the secant line to approximate the root of the function. So let us consider a function f of x and choose two initial points xi and xi minus 1 on the graph so that we can define a secant line. These 2 points define a secant line that passes through the points xi, f of xi and xi minus 1, f of xi minus 1. Specifically, the next point, or the estimate, the xi plus 1, is obtained by computing the x value at which the secant line passing through the points xi, f of xi minus 1, f of xi minus 1 has a y coordinate of 0. When we talk about the derivation, the next guess formula in secant method can be derived by using the geometric similar triangles concept. Here we can see the two geometrically similar triangles AEB and DEC. By side length proportionality, we can write AB by AA equals DC by DE, which then can be written as f of xi by xi minus xi plus 1 equals f of xi minus 1 by xi minus 1 minus xi plus 1. On rearranging, the secant method is given as xi plus 1 equals xi minus f of xi into xi minus 1 by f of xi minus xi minus 1. Now, let's take a look at an example problem that we can solve using the secant method. Suppose we want to find the minimum diameter of a shaft that can withstand a given torque T and length L, given that the maximum shear stress tau max and yield strength S yield are known. To solve this problem, we will use the secant method, a numerical optimization algorithm that uses the slope of a secant line to approximate the root of a function. In this case, the function is the torque equation, T equals pi by 16 tau max into d cube, where T is torque, tau max is the maximum shear stress, and d is the diameter of the shaft. For our initial guess, we will use d1 equals 55 mm and d2 equals 60 mm. We can calculate the torque at these two diameters using the equation above. Using these values, we can then compute the next diameter estimate d using the secant method formula d equals d2 minus t2 into d2 minus d1 by t2 minus t1. We can then iterate this process until we reach a diameter estimate that gives us a torque close to the required 10 kN. Now let's go through the iterations together. When we see the iteration 1, we take d1 equals 55 nanometers and 60 millimeters. We then compute t1 and t2 by using d1 and d2, and then estimate the diameter d equals d2 minus t2 into d2 minus d1 by d2 minus t1. So there we can get a d. Coming to the first iteration, we take the initial guesses d1 equals 55 mm and d2 equals 60 mm. We then calculate torque T1 and T2 by using d1 and d2, and then we find the estimate of the diameter by using the formula d equals d2 minus t2 into d2 minus d1 by d2 minus t1. And then we compute the torque by using the estimate, which gives us 10,903 nanometers in the first iteration. Since the calculated torque is greater than 10 kN, we need to decrease the diameter for the next iteration. Similarly, in the second iteration, the calculated torque is greater than 10 kN. So we again need to decrease the diameter for the next iteration. So in the third iteration, the initial guesses become d1 equals 55 millimeters and d2 equals 56.19 millimeters. We then calculate t1 in d2 by using d1 in d2, and then calculate the estimate of the diameter d, which gives us 55.82 millimeters, and then we compute the torque at d equals 55.82 millimeters, which gives us 9981 nanometers. Since the calculated torque is now very close to 10 kilonanometers, we can stop here and conclude that the minimum diameter required to transmit the torque safely is approximately 55.82 millimeters. We now implement the secant method for the above problem using Python. We first define a function, secant method, that takes in 4 arguments. Func, the function to find the root of. X0 and X1 are the first and the second initial guesses for the root. The tolerance for the root finding algorithm with the default value of 1e minus 6, and then the maximum number of iterations for root finding algorithm with the default value of 100. We then employ a for loop, which will iterate max iter times or until the root is found within the tolerance value. Within the loop, we find the function values at x0 and x1, and then we compute the estimate of the next guess, that is x next, which is the intersection of the secant line through x0, f of x0, and x1, f of x1 with the x-axis. And the next line checks if the new guess for the root is within the specified tolerance TOL, if the function returns x next as the root. And then we update the roots as x0, x1 equals to x1, x next. In the next block of the code, we define a function known as minimum shaft diameter that takes in 4 arguments, T, L, Tomax, and S yield, which are the torque applied to the shaft, the length of the shaft, the maximum shear stress allowed in the shaft, and the yield strength of the shaft material. And the next lines, T equals 1e3, Tomax equals 1e6, and S yield equals 1e6. These lines convert the torque, maximum shear stress, and yield strength from their given units to Newton millimeter and Newton millimeter square respectively. In the next block of the code, we define a function func that takes in the diameter d of the shaft and returns the difference between the shear stress in the shaft due to the applied torque and the maximum available shear stress Tomax. In the next line, we compute the cross-section area and polar moment of inertia of the shaft given its diameter d. And also, we compute the shear stress tau in the shaft due to the applied torque T with the formula tau is equals T into D by 2 into J. The next 2 lines set the initial guesses for the diameter and define a new function funcd, which converts the output of function to a stress ratio, which is the difference between the shear stress and maximum available shear stress divided by the yield strength. And then the secant method function is called with funcd, d0, and d1 as its input parameters. This function returns the minimum diameter of the shaft that satisfies the stress constraint. Finally, the minimum diameter is returned as the output of the minimum shaft diameter function and printed in a user-friendly way. So for the above given inputs, the output is minimum shaft diameter gives as 0.0609 millimeters. But when t equals 0, then an error occurs called zero division error because the denominator becomes 0. So for the above given inputs, the output will be 0.0609 millimeters. And when t equals 0, that is when torque equals 0, the denominator in the formula becomes 0. So it gives an error called as zero division error, which you can see clearly when we execute the code in a Python compiler. Now let's execute the code in a Python compiler where we take the initial guesses as 55 millimeters and 56 millimeters. Let's run the code. For the taken inputs, the minimum shaft diameter given as 60.9 millimeters. Here a problem arises when torque becomes 0. Let's see by running the code again. Here an error occurs called zero division error because in the denominator the torque becomes 0. This problem can be overcome by assigning torque a small value in the order of tolerance. When we talk about the applications in which secant method is used, minimum shaft diameter and the secant method are important tools in the design of rotating machinery. The minimum shaft diameter is a crucial parameter because it determines the ability of the shaft to withstand bending and torsion stresses induced by the applied torque. For example, in an engine, the crankshaft must be designed to handle the torque generated by the combustion process. If the shaft diameter is too small, it may fail under the applied stress, causing catastrophic engine failure. On the other hand, if the shaft diameter is too large, it will increase the weight and cost of the system unnecessarily. The secant method is a simple and efficient way to optimize the shaft diameter. It can be used in a variety of rotating machinery applications such as motors, turbines, and gearboxes to ensure that the shaft can handle the applied torque without being too heavy or expensive. These are the references I took the matter from. Thank you.